Let's continue now. In the last video, we started doing some problems on the material that we have covered so far about rings, ideals, maximal ideals and so on. So I ended the last video with a problem about, I think this is the second problem maybe, or third problem, and we have done the first part. So recall for problem 3, the assumption was R any ring, ij two ideals such that ST stands for such that ij is equal to R. We have shown that earlier in the last video. We showed the product is equal to the intersection. Now the second part, so let me write it in a different slide. Second part is an important, it's a famous result in mathematics called Chinese remainder theorem. So it has this name, and what does it say? So second part is to show that for all a comma b in R, for all elements, for any pair of elements a comma b in R, there exists, I'll write it as a theorem, there exists x in R, given two elements a comma b in R, there exists an element x in R such that x minus a is in I and x minus b is in J. So you understand what I am saying? Given two elements of R, there is a single element R which when you subtract A, it is in I, and from the same element when you subtract B, which it is in J. So for those of you who know a little bit about language using residues and modulos of ideals, this is same as saying that x is A modulo I. X is congruent to A mod I. This says that x is congruent to B mod J. Okay, this is just notation. If you are not familiar with it, don't worry about it. All I am saying is that there is a single element x which is like A in some sense in the quotient ring R mod I, because x minus A is like A, x is like A. X minus A is 0 modulo I. So x is same as A mod I, x is same as B mod J. Given any two elements, we can do this. The solution or the proof is the following. Again, we use the hypothesis. Remember, the hypothesis that I plus j is equal to R was made, and this is very crucial. We use that hypothesis I plus j is equal to R. So remember, I plus j is equal to R means every element of R can be written as a sum of element of A and an element of J. So in particular, we can apply this to R, A. So write A is equal to R plus S, B is equal to U plus V. So A is an element of R, given element, remember A and B are given in R. I write A as R plus S, B as U plus V, and what do you know about R? It's in I, S is in J. Similarly, U is in I, V is in J. So that's the point. Every element of the ring R can be written as something in I plus something in J. So I write A as R plus S, B as U plus V. And now I claim that, now I will tell you how to choose X. So let us choose X to be, I am defining X to be S minus U. Okay. So I claim that this X works. What does it mean? Remember, the theorem is asking us to show that there is an X with certain properties. I have chosen that X, and I am going to show that that X has the required properties. What are the required properties? We need to check that they are on the notes here. So we need to check x minus a is in I and x minus b is in J. So let's check these two things. So x minus a, x is s minus u. This, remember, that's my choice for x. So x minus a is s minus u minus a. But what is R? Sorry, what is A? A is R plus S. So S minus U minus A is S minus U minus R minus S. Correct? So S minus U minus R minus S. Of course, I can cancel S. So this is minus U minus R. But U and R are both in I. R is in I, U is in I. So this is also in I. If you have U and R in I, minus U is in I, minus R is in I, their difference is in I. So x minus A is in I as we are required to show. Now what is x minus B? X minus B is S minus U minus B, and B is U plus V. So S minus U minus B is S minus U minus V. This is, now I cancel U. This is S minus V. Now where are S and V? S and V are in J. So this is in J. So x is in I and x is in J. So sorry, x minus I is in A and x minus B is in J. So x minus I is in I, x minus B is in J as required. Okay, so this may seem like, how did I think of x to be this? But that is just by playing with it, the required conditions. It's not difficult to see that x equal to S minus U works. So this is the Chinese remainder theorem. So solution is complete. You may have seen Chinese remainder theorem in the case of integers. So this is the generalization of that to arbitrary rings. So I want to now rephrase the statement of Chinese remainder theorem in a more conceptual manner. So I want to write Chinese remainder theorem, not the proof but the statement, Chinese remainder theorem differently as follows. Okay, so now this is what I want to do. So consider quotient ring R mod I and R mod J and the product ring. This is the product ring. I believe I mentioned product rings before, but otherwise it's not difficult to see what the operations are here. If you have two rings, you take the Cartesian product. So elements are just pairs of elements, one from the first ring, the other from second coordinate is from the second ring, and multiplication and addition happen coordinate wise. So the 0 element is 0, 0, multiplicative identity is 1, 1, and if you have a, b times c, d, you have ab, ac, bd. Okay, so this is easily seen to be a ring. So take the product ring and I will define a homomorphism from R to the product ring. I define phi of A to be A plus I, B plus J. Sorry, A plus J. So write Chinese remainder theorem differently as follows. So first of all, I am defining a set map R to R cross I, R mod I cross R mod J, where I send a ring element to the residues of that ring element in R mod I and R mod J. And it's an exercise which I will not do and I will ask you to do. This is a very easy exercise. It is that phi is a ring homomorphism. Now Chinese remainder theorem has a very nice formulation which is easy to remember in terms of this homomorphism. Chinese remainder theorem, let's call this CRT. So CRT, it's a standard abbreviation for Chinese remainder theorem. It says that the above map is surjective. The above map is surjective, which is not clear a priori because you are taking the map from R to R mod I cross R mod J, which sends A to A plus I, A plus J is the same element. In general, to be surjective, you take an arbitrary element of the product, right? So this is an R mod I cross R mod J. In order to be surjective, there must be an element X which maps to that. What is this X? Right? In order for a map to be surjective, take any element in the range, the codomain ring, in this case R mod I cross R mod j. Every element is in the range. So A plus I comma B plus j must be an element in the image. That means it must come from X, some X. And Chinese remainder theorem is telling you that X, what that X is. Take the X that comes from Chinese remainder theorem. Now, what is the property of that X? X minus A is in I. But if X minus A is in I claim that X plus I is equal to A plus I. If X minus A is in I, in the quotient ring R mod I, X and A are basically same elements. The residue of X is same as residue of I. Similarly, X minus B is in J by the Chinese remainder theorem. That means X plus J is B plus J. Now, what is phi of X? Phi of X is X plus I comma X plus J. By definition, any element goes to that element plus I comma that element plus J. That means it goes X goes to X plus I comma X plus J. But I just proved that X plus A is A plus I and X plus J is P plus J. Okay. So, every element, you start with an arbitrary element. This is an arbitrary element of the product ring. Take an arbitrary element and I have shown that it has a pre-image. That means it is surjective. So, it is convenient to remember Chinese remainder theorem as saying that if you have two ideals in a ring I and J whose sum is R, that is the whole point here, I plus J is R, then the map, natural map from R to R mod I cross R mod J is a ring homomorphism, is a surjective ring homomorphism. As a bonus question, I am going to ask you, what is the kernel of phi? Remember, phi is the map from R to R mod I cross R mod J. It is a surjective ring homomorphism by the previous problem. So, what is the kernel? Remember, kernel of any ring homomorphism is all elements of the ring such that phi A is 0. But in our context, that means it is all elements A such that A bar, A plus I is 0 plus I and A plus J is 0 plus J. But that means all elements A in R such that A is in I and B is in J. Because A plus I is equal to 0 plus I means A is in I, A plus J is equal to 0 plus J means B is in J. But what is, there is another name for the set of elements A such that A is in I and B is in J. And what is that? That is simply the intersection. So, the kernel is intersection. So, we understand now everything about this map, R mod I to R to R mod I cross R mod J. So, this is surjective, that means image is all of R mod I cross R mod J and kernel is I intersection J. Okay, so, this is a useful problem to keep in mind, and again I will reiterate the crucial hypothesis that I plus J is equal to R is important, and it is a good exercise for you to think of an example where this map is not surjective, and example where I plus J will not be equal to R and this map is not surjective. Now, what does the first isomorphism theorem say? So, I want to complete this circle of ideas by stating what is the implication of first isomorphism theorem. You have a ring homomorphism which is surjective and its kernel is I intersection J. So, R mod I intersection J is isomorphic to R mod I cross R mod J. So, this is a very important statement that we will sometimes use. If I plus J is equal to R, the quotient ring R mod I intersection J is just the product ring R mod I cross R mod J. So this is the conclusion of the Chinese remainder theorem in some sense. Okay, so now I'll continue with the problems. So the next problem I want to do, maybe the fourth problem, is I want to first list, this is maybe some of these we have done, find the maximal ideals, find in some sense the all the maximal ideals. Of the following rings. So 1 Z, 2 the ring Rx mod, the quotient ring Rx mod x squared, the ring Rx mod x squared plus 1, and finally the ring Cx mod x squared plus 1. Okay, so there are 4 rings here. I want to find the maximal ideals of this. So the first one is easy. We know prime ideals, I may have said this before, prime ideals of Z are the 0 ideal and Pz where P is prime. Because a maximal ideal is automatically prime, the maximal ideals will be among these, right? If some ideal is not prime, it cannot be maximal. So in order to find the maximal ideals of Z, we need to first start with prime ideals and see which of those are maximal ideals. Now which of these are maximal ideals? Is 0 a maximal ideal? This is not a maximal ideal. Why is that? By definition, a maximal ideal is an ideal which is not contained in any proper bigger ideal. 0 is certainly not like that because 0 is contained in 2Z. So in 2Z is a proper ideal. 0 is properly contained in 2Z. So 2Z is not the 0 ideal. So this is not a maximal ideal. What about this? These are maximal ideals. There are several ways of doing this. Pz cannot be contained in a bigger ideal, or equivalently Z mod Pz is a field. So we have shown that, we recall I in R is maximal if and only if the quotient ring R mod I is a field, right? And in this context, it's also, I'll recall for you, though we don't need this here, I in R is prime if and only if R mod I is an integral domain. So to check maximality, we want to quotient by the ideal and check if it's a field. And this is an exercise, I have said this a few times before, Z mod Pz is a field. You take any non-zero element of Z mod Pz, show that it has a multiplicative inverse. So it's a field. So what are the prime ideals of, maximal ideals of Z? So max ideals of Z, max ideals of Z are Pz where P is prime. So any ideal generated by a prime number is a maximal ideal. So now let's look at the second one. So look at Rx mod x squared. Okay, now in order to determine the maximal ideals of this, I am going to recall for you the correspondence theorem. What is correspondence theorem say? So it talks about R and R mod I. So R is a ring, I is an ideal. And what is the statement of the correspondence theorem? It says that there is a bijective and inclusion preserving. You understand what I mean by that, right? Map. Inclusion preserving map means if there is a map between ideals. So ideals of R containing I So this is a bijection. Inclusion preserving bijection from ideals of R containing I to ideals of R mod I. So inclusion, so there is a bijection we have seen, and why is it inclusion preserving? If J1 is a J1, J2 are ideals that contain I, and J1 is contained in J1, J2 both contain I, and the corresponding, let me write it like this, ideals also have the same inclusion. In other words, the inclusion of J1 in J2 is preserved. So I am going to use this correspondence theorem. So what are ideals of this quotient ring? Ideals are in bijective correspondence with, so let me say ideals of this come from ideals of Rx that contain x, right? Rather I should say x squared. So ideals of Rx mod x squared come from ideals of Rx. So there is a map from Rx to Rx mod x squared, and ideals in the ring Rx mod x squared are actually images of ideals of Rx which contain x squared. So let I be an ideal containing x squared. Remember, we are actually interested in maximal ideals of Rx mod x squared. The fact that this bijection is inclusion preserving means the bijection also gives a bijection between maximal ideals of R that contain I and the maximal ideals of R mod I. So this bijection restricts to a bijection of the subset here in this first set of maximal ideals containing I, and it gives a bijection to the maximal ideals of R mod I. So we can further assume that I is actually maximal ideal. So assume that I is a maximal ideal. So if I is a maximal ideal containing x squared, so I is in fact prime also, right? A maximal ideal is prime. This we have shown earlier. And I is a prime ideal, and x squared, the ideal x squared is contained in I means the element x squared is contained in I. But prime ideals have the property that if a product belongs to the ideal, one of the elements belongs to ideal. X squared belongs to I means x is in I. That means the ideal generated by x is in I. Remember, I is an ideal, it contains x, that means it contains the entire ideal generated by x. On the other hand, it's an easy exercise for you. The ideal x is maximal in Rx. So I will leave this as an exercise. Show that is a maximal ideal of actually this is not quite required for us. In any case, yeah, I think this is required for us. So the idea is to show that, so the hint, take some ideal x, j containing x contained in Rx. Okay, so then and argue that if j is not equal to x, then j contains a polynomial, let's say fx. Remember, Rx is the polynomial ring. So these are polynomials in one variable x. So j I claim contains a polynomial of the form an xn, an minus 1, xn minus 1, a1x plus a0, and a0 is not 0. So if j is not equal to the ideal x, argue that it must contain an element of this form, because if it does not contain an element of this form, it is equal to x. And once you argue this, then show that A0 is in J and hence J is equal to Rx. Okay, this is almost a complete hint for you. Using this, you can show that X is a maximal ideal. So now let's go back here. We have shown that the ideal I contains X, but X is maximal. So remember, a maximal ideal, and I is, remember, a proper ideal, because I is a maximal ideal and maximal ideals are by definition proper ideals. So X is a maximal ideal, it is contained in I is a proper ideal, so the only possibility is I is equal to X. Hence we have concluded that the only maximal ideal of Rx containing x squared is the ideal. Okay, so the only maximal ideal of Rx containing x squared is x, which implies by the correspondence theorem, so the only maximal ideal of Rx mod x squared is the ideal x plus I. So this is my notation for the image under that correspondence. Another equivalent notation is x plus x squared, I should write. This is bad notation, but okay. So in particular, there is exactly one maximal ideal of Rx mod x squared, and it is given by the ideal x. Okay, so this is a bit involved, this proof. It uses several facts. So please go over this carefully, repeat this video if you want, and make sure that you understand this statement. We are interested in finding the maximal ideals of the quotient ring Rx mod x squared, and we have showed that there is exactly one such, and that comes from the ideal x in Rx. Okay, now that leaves two more rings. So I will stop the video now. I will continue the next video with these two examples. What I want you to do before you watch the next video is to recall the proof of Rx mod x squared, think about it carefully, and using that try to solve these two remaining problems. Similarly as Rx mod x squared, to determine the maximal ideals of Rx mod x squared plus 1, you need to figure out the maximal ideals of Rx that contain the ideal x squared plus 1. Similarly, to determine the maximal ideals of Cx mod x squared plus 1, you need to determine the maximal ideals of Cx that contain x squared plus 1. Okay, so I will leave that calculation for you and I will solve it in the next video. So I will end this video with an exercise of a statement that we have used. I have said it, but I want to emphasize it. So I will keep this as an exercise for you to do. So let R be a ring and let I be an ideal. This is a refined version of the correspondence theorem. So the statement is there is an inclusion preserving bijection between the following two sets. There is an inclusion preserving bijection between the following two sets. What are they? Maximal ideals of R containing I. So these are maximal ideals of R that contain I. And on the other side we have maximal ideals of R mod I. Okay, so if you remove the word maximum, maximal in both these sets, this is exactly the correspondence theorem. Ideals of R containing I are in bijective correspondence with ideals of R mod I. But now I am saying that I can add the adjective maximal and the inclusion preserving bijection still exists. So now I might as well write this, though we don't need it in the previous problem. There is such a bijection also from prime ideals of R containing I, and here also you put prime ideals of R mod I. What you have to do for the first one is easy, because maximality is a statement about inclusions. All you need to do is that the original correspondence theorem is an inclusion preserving bijection. So that gives the statement 1. For the second statement, you have to use a little more ring theory. It says that you take an ideal of R containing an ideal of R containing I. Suppose it's prime. The corresponding ideal of R mod I is also prime, you want to show. And similarly, if you take a prime ideal of R mod I, the corresponding ideal of R containing I, which exists by the correspondence theorem, is actually prime. So one you prove right now in order to understand the solution for the exercise here, Rx mod x squared, and use it in the third and fourth exercises. So which I'll come back to in the next video. The statement about prime ideals also we will come back to in the next video and formally prove this statement. So please go over these solutions carefully. These are important and subtle statements about rings and ideals and prime ideals and maximal ideals, and hopefully you will understand everything that I said after watching it if needed. So I'll stop the video here. In the next video we'll continue with more problems. Thank you.